Hello everyone. Today is the third session for the chapter chemistry of D and F block elements. Today we will end the portion of the D block elements and we will move towards F block elements from the next session. So today we will basically discuss the magnetic properties, the colors of transition metals, and such kind of properties of transition metals one by one. So firstly, the question is calculate the magnetic moment of a divalent cation having an atomic number of 28 in aqueous solution. So whenever we will talk about this magnetism or the magnetic properties of D block elements, so we have to have a brief idea about their magnetic properties. So when a specific magnetic field will be applied on a transition metal, so this will be the case. So suppose this is a transition metal and a specific magnetic field has been applied on it. This is a magnetic field. So when a magnetic field is applied to a transition metal, so mainly two types of magnetic behavior we will see. First one is the diamagnetic behavior and the second one is the paramagnetic behavior. So first one is the diamagnetism and the second one is the paramagnetism. So diamagnetic substances are those which are actually repelled by the applied magnetic field. So whenever we are applying this magnetic field, the diamagnetic compounds will not be attracted towards the magnetic field, rather they will be repelled. And the paramagnetic substances are thus the opposite. So they will be attracted towards the applied magnetic field. So these transition metal cations have both these kind of properties depending upon their number of unpaired electrons and so on. So now the diamagnetism and the paramagnetism are the major two categories. But when these substances are very strongly attracted, these are called ferromagnetic substances. So actually, ferromagnetism is an extreme case of paramagnetism. So all ferromagnetic substances are paramagnetic in nature, but all paramagnetic substances are not ferromagnetic in nature. And diamagnetics are those which are repelled by the applied magnetic field. These two are actually attracted by the applied magnetic field. Paramagnetic compounds are those which are actually attracted, and many transition metal ions here will be paramagnetic. But if a compound is very strongly attracted to the applied magnetic field, this is called the ferromagnetic. So this is called ferromagnetism. So all the paramagnetic compounds are not ferromagnetic compounds, but all the ferromagnetic compounds are indeed paramagnetic compounds. So this was a brief introduction about the magnetism or the magnetic properties of a transition metal. Now, how we will calculate the magnetic moment of a transition metal cation. Now, you know that transition metals all possess, or most of them possess, some unpaired electrons. Now, these unpaired electrons are actually responsible for the magnetic moment of the substance. So let me show you with the help of an example. So we are having this electron. So an electron is actually having a magnetic moment. Now this magnetic moment is actually having contributions from two important parameters. First one is the spin angular momentum and second one is the orbital angular momentum. So first one is the spin angular momentum, second one is the orbital angular momentum. Now the compounds which we are talking about, so the transition metal compounds, are actually having no significance from the orbital angular momentum because they are actually quenched. So since this orbital angular momentum is actually effectively quenched, so there is no significance in talking about orbital angular momentum. So all we will discuss about is the spin angular momentum. So spin angular momentum is mainly responsible for the magnetic moment of a transition metal. Now here is the formula to calculate the magnetic moment of a transition metal cation. So we are having this mu. Mu stands for nothing but this magnetic moment, and this suffix SO stands for the spin only angular momentum or spin only magnetic moment. So mu SO, mu is calculated as root over of n into n plus 2 Bohr magneton. So Bohr magneton is the unit of magnetic moment to calculate the magnetism of the transition metal, and n is nothing but the number of unpaired electrons in the system. Mu is the magnetic moment, SO stands for the spin only value, n is the number of unpaired electrons, and Bm is nothing but Bohr magneton. Now Bohr magneton is the unit of this magnetic moment. A single unpaired electron will have a magnetic moment of, so when n is equal to 1, it will be calculated as root over of 1 into 1 plus 2. So that is 3. Root over of 3 is 1.73 Bohr magnetons. So this is the basic formula to calculate the spin only magnetic moment of a transition metal. Now we shall jump to the question. So the question says, when the atomic number is 28, what is the magnetic moment? Now you see, when the atomic number is 28, so we will have this 4s2 d6 orbital angular this 4s2 d8 orbital angular calculation. So when the electron configuration will be d8, so 28 will actually count for d8, because up until 20 it is calcium, and after calcium we are having 8 electrons. That's why the configuration is d8. So we shall actually fill up the electrons in the cell as having 1, 2, 3, 4, 5, and then we will pair up the electrons 6, 7, and 8. So actually we are having 2 unpaired electrons in a d8 configuration. So number of n is equal to 2. So simply what we will do, we will put 2 in the given equation. So we will calculate as root over of 2 into 2 plus 2. So it will be root over of 2 into 4. So it will be root over of 8 Bohr magneton. So that is actually 2.84 Bohr magneton. So the magnetic moment of the divalent cation, which is having the atomic number 28, is 2.84 Bohr magneton. Now here comes the question, what is the cation? The cation is nothing but nickel plus 2. Nickel plus 2 is d8, because the 4s electrons will be gone, because it is a plus 2 cation. So the last electrons, the valence electrons, are 4s electrons. So nickel 2 is nothing but d8 system. So the nickel 2 cation will have a magnetic moment of 2.84 Bohr magneton. So this is the basic equation that is very much helpful for you guys to remember. So when we will be able to calculate the other number of unpaired electrons of the transition metal cations, we will be able to calculate the mu SO value or the spin only magnetic moment value with the help of this equation, which is mu is equal to root over of n into n plus 2. Now we shall move towards the next question. So the next question is regarding some different topic. It is regarding the color of the transition metal in aqueous solution. So the question is, which among the following ions are found colorless in aqueous solution? Options are manganese 3, cobalt 2, scandium 3, nickel 2, and titanium 4. So these are the given options. Now, how this color actually generates in case of transition metals? So what happens when there is an electron in the d orbital? Suppose there is an electron in the d orbital here, the electron. Now, when we are actually giving some external energy, it is excited to an upper energy level. So when an external energy is applied, this electron will be excited to a higher energy d orbital. Now, this is the energy of excitation, the gap between this d orbital and this d orbital. So now the energy of excitation actually corresponds to the frequency of light absorbed, because the energy, this electron will absorb light, absorb energy from the given light, and it will be excited to the higher energy d orbital. Now this frequency generally lies in the visible region. The energy E associated with the process will be equal to h nu, where nu is the frequency of the absorbed light. Now the color it is actually absorbed, and when it will be emitted is determined. Emitted is the complementary color, because which color, the color that will be absorbed, the complementary color will be emitted. Now this complementary color is actually determined by the nature of the ligand. Suppose a metal complex is here, which is termed as MLN. And M is the transition metal and L is the associated ligand. So depending upon the nature of the ligand, the value of nu actually will be determined. So here in most of the cases, I have in this question also, I have actually depicted it is an aqueous solution. So the metal complexes will be M H2O whole X N plus, where N is the oxidation state of the metal, because H2O is a neutral ligand, and X is the number of water molecules that are associated or attached with the metal complex. So we will talk about this M N plus system, where H2O is the ligand, because it is an aqueous solution that we are talking about. Now, depending upon the energy of excitation of the electron, the color will be shown. So it all depends upon the unpaired electrons on the metal system. So every transition metal cation that is having an unpaired electron will be actually able to show such colors. Now let's come to the typical question. So this question we are talking about, so we will see what are the electronic configurations of the given cations. So first one is the manganese 3. So manganese 3 is a D4 system, which is indeed having 4 unpaired electrons. Next we have cobalt 2. So cobalt 2 is a D7 system. So if we draw the electrons of cobalt 2 in a D7 manner, we will see it is having 1, 2, 3, 4, 5, and then we will pair up the first 2 electrons, 6 and 7. So we will have 3 unpaired electrons in case of cobalt 2. Now there comes scandium 3. So scandium has an electronic configuration of 4s2 3d1. So scandium 3 will be D0. Nickel 2, we have already discussed in the last question, is a D8 system, which is having 2 unpaired electrons. And last one is the titanium 4. So titanium 4 and scandium 3 are isoelectronic. So it is also D0. Now you see the scandium 3 and titanium 4 are such two systems which are actually not having any unpaired d electron. Since they are having this D0 configuration and they are actually not having any unpaired electrons, so in that case the excitation of energy of the electron is not seen or not observed here. That's why these two ions are actually found as colorless, because the electrons are responsible for the color, and since they are having this D0 configuration, they are having no electrons. That's why they are colorless in aqueous solution. Now we shall move to the next question. So the next question is, give some examples of complex formed by transition metals. So this is an basically informative question for you. So these are the question, which are the complex compounds that are actually formed by the transition metals. Now transition metals are capable to form a variety of complex compounds. So which are actually complex compounds? So when the metal ions will actually bind with a several anionic or neutral or cationic molecules. So a transition metal is there, and it will actually find several kind of ligands. So ligands can be cationic, ligands can be anionic, or ligands can be neutral. So with this kind of, when this transition metal will bind with several this kind of ligand and will form such complex as Tm and Ln. So these are actually called the complex compounds. So when this transition, the chemistry of these complex compounds will actually be discussed well in the coordination compound chapter, which I will discuss later after finishing this D and F block elements. But for the time being, I will discuss why these transition metals actually form a large variety of these complex compounds. So first one is these transition metals are comparatively smaller in size. You see from left to right, because the d orbitals are very poor shielding, so these sizes of the transition metals actually decrease. That's why they have very smaller size and they have very high ionic charge. Now, when they are having a high ionic charge and they have a smaller size, then their ionic potential value, that is phi value, is quite high. Since this ionic potential value or the phi value is quite high, that's why they are actually having very high charge density. So they can attract several kind of ligands to the metal core. And lastly, these transition metals have this very good power of d orbitals, which are mostly vacant. So any ligand can come up and take up the place of the vacant d orbital, and they can bind to the d orbital. So that's why transition metals actually form a large variety of complex compounds. So you see here, I have actually given typical examples of which kind of ligands are actually attached to the transition metals. So first one is the iron ferricyanate system, which is FeCN6 3-. You see here the oxidation state of iron is +3. And you see 6 cyanide ligands are actually bound to the central Fe3+ system, and it has formed this compound. This compound is actually K3FeCN6, which is termed as potassium ferricyanide. The second one is the PtCl4 2- compound. Here you can see the oxidation state of the central platinum ion is 2+, and 4 Cl- ions are attached to the Pt2+ center. So it is a chloroplatinate. Next one is the copper NaH3 2+, a tetramine copper system. Copper is in +2 oxidation state because ammonia is a neutral molecule, and you see it is tetramine copper 2+ system. Last one is the nickel tetracyano compound. Here you can also see just like the first one, the oxidation state of nickel is +2, and cyanide ligands are there. 4 cyanide ligands are there. So +2 - 4 is actually counting towards the di-negative charge. So this compound is the cation of potassium. So the compound is K2NiCN4, potassium tetracyanonickelate. That is the compound. So basically there are 3 points because of which these transition metals actually form a large variety of complex compounds. First one is the smaller size. Second is the high ionic charge, that is actually the high ionic potential value. And last one is the d orbital here. So the availability of the d orbital to have a bond or form bonds with the ligands. So that's why transition metals actually form a variety of complex compounds. The next one is the give an example of a transition metal which is actually able to catalyze a chemical process via change of its oxidation state. So here you can also take up a different kind of property of a transition metal, which is the catalytic property. So transition metals have this unique kind of ability to catalyze a chemical process. So catalytic property is actually one of the major properties that are shown by a transition metal ion. They are actually known for their catalytic activity. So this activity is actually ascribed to the fact that they are able to adapt different kind of oxidation states and to form different kind of complexes. So in the last question I have told you, like these transition metals are capable to form different kind of compounds, complex compounds, and they actually can form several oxidation states. So they suppose they are having class X, where X actually can vary from 0 to a positive integer, 0, 1, 2, and so on. So these transition metals have this unique ability to adapt multiple oxidation states and also to form a variety of complexes. Now, you can have typical examples here. In contact process, vanadium oxide, which is the V2O5, is actually a catalyst in contact process. Also, finely divided iron in the Haber-Bosch process to form ammonia, it is also a catalyst. Also, nickel, Rani nickel is one of the very much well-known catalyst for hydrogenation, catalytic hydrogenation of olefins. So these are the basic examples of the transition metals which are acting as a catalyst. Now, catalyst, when we are talking about, so 2 kinds of catalysis are known. First one is the homogeneous catalysis, and second one is the heterogeneous catalysis. So here I have actually talked about the heterogeneous catalysis mainly. So in case of heterogeneous catalysis, a solid surface is there, and when there will be an involvement or the bond formation will be happening between the reactant molecules and the atoms of the surface of the catalyst. Now, this has the effect of increasing the concentration of the reactant molecule on the surface of the catalyst, and also weakening of the bonds of the reactant molecules occur. So both these things occur simultaneously. The activation energy or the barrier to actually cross to perform a typical reaction is actually lowered, and that's why they become more effective in the catalysis platform. So now there is a typical example when I have actually talked about the homogeneous and the heterogeneous system. In homogeneous system, the metals of the catalyst is actually soluble with the reactant molecule in the reaction pot. In case of heterogeneous system, on the surface of the catalyst, the reaction occurs. So this is the basic difference between the homo and the heterogeneous catalyst. But in case of homogeneous catalyst, though the yield is quite high, but the separation of the catalyst from the reactant molecule is bit tough because all the things are soluble in the solvent. But in case of heterogeneous catalyst, the separation is actually quite good. So we can actually take up the catalyst back and do some trial runs with the regenerated catalyst also. So here the question is actually saying, give an example of a transition metal ion which is catalyzing a chemical process by the change of the oxidation state. So we are having this reaction. 2 moles of iodide is actually reacting with S2O8 2 minus. It is a part disulfate anion, and the products are iodine, that is I2, and 2 moles of sulfate. So what is happening here? This is a redox reaction which is catalyzed by iron 3. Here you can see the iodine's oxidation state is -1, and in this case the oxidation state of iodine is 0. So iodine is actually oxidized here. So it is the reducing agent. So, so 2 moles of sulfur are there, and we are having 8 oxide. So if we can draw the oxidation state of sulfur as X, so 2x minus 16, 16 comes from 8 into -2, -2 is coming from oxygen, is equal to -2. So X is actually here +7. So the oxidation state of sulfur here is +7, and in sulfate it is +6. So this part disulfate is reduced to sulfate, and iodide is oxidized to I2. So we are having this explanation of how iron 3 is actually able to catalyze the reaction. You can see here the iron 2 is oxidized by iodine to iron 3 plus. So iodide is actually oxidizing iron 2 to iron 3, and itself is getting oxidized to I2, and this Fe3 plus will then react with the S2O8 2 minus, that is part disulfate here. And you can see here Fe3 plus will be reacting, and this Fe3 plus will react with A2I minus to form Fe2 plus plus I2, and then this generated Fe2 plus will react with S2O8 2 minus, that is the part disulfate, and it will again get oxidized to Fe3 plus, and sulfate will be released. So that is the entire equation here, that is actually catalyzed by iron 2. Now we shall move to the next part. So this question is, name some interstitial compounds that are formed by transition metals. So what are these interstitial compounds? So the interstitial compounds are those which are formed when small atoms like carbon, hydrogen, or nitrogen. So these are the atoms here which are actually small in size. They will actually get trapped inside the crystal lattice of the metal. So here say we have this crystal lattice of a metal center. So here we have a crystal lattice, and you see when these atoms will be trapped inside the crystal lattice of the metal center. So when these small atoms will be considered, so any large atom cannot be penetrated or trapped inside the cavity of the or the lattice of the transition metal. But here you can see the atoms involved are hydrogen, nitrogen, carbon, hydrogen. So these are the actually atoms which are actually trapped in the crystal lattice of the metals. So in this case, these are actually non-stoichiometric. They are neither ionic in nature nor very much covalent in nature. So these are the examples. First one is a titanium C Fe3H VH 0.56, titanium H 1.7, Mn4N. So these are the formulas. So these formulas do not actually count to any kind of formal oxidation state of the metal. You cannot say here the oxidation state of titanium here is plus 1.7. No, not here also. The oxidation state of vanadium is not plus H 0.56. Nor in this case, iron is having the oxidation state of plus 1.3, nor in this case titanium is having a plus 1 oxidation state or plus 4 oxidation state. So these values or these formulas are not actually corresponding to any normal oxidation state of the metal. So because the nature of the compounds, these compounds are termed as the interstitial compounds because they are inter between ionic or covalent. In this case, the atoms are actually inter between the crystal lattice of the metal centers. So that's why they are termed as the interstitial compounds. So these interstitial compounds have some other properties also. First one is they have very high melting points rather than the pure metal. So titanium C has a melting point higher than TiC. Fe3H has higher melting point than iron. Such as these three compounds also have higher melting points than vanadium, titanium, and manganese respectively. Secondly, they are actually very hard in nature. Some borides even approach diamonds in their hardness. The third and first one is that they have their metallic conductivity intact and they are actually chemically inert molecules. So that's why their reactions or chemical reactions are not that much prominent in nature. Now we shall come to the next question, which is regarding alloys. So regarding alloys, you all have encountered which are the alloy. So alloys are nothing but blend of the metals prepared by the mixing by the components. So whenever we are talking about alloy, we are having this M1 and this M2. So this M1 and M2 will have a specific composition. So they can be homogeneous solid in which metals are actually distributed randomly inside one another. Such alloys are formed by atoms with the metallic radii that are within about 15% of radius with each other. So when the size gap between these two metals are more or less 15%, they are called the homogeneous alloys. But there are when the alloy radii will actually differ quite drastically, so they will actually have similar non-similar kind of alloys. So now different kind of alloys are actually known. The most popular ones are brass and bronze. So brass is the one which is having one transition metal and another non-transition metal. And bronze is having one transition metal, another non-transition metal. It is the p block element. So here you can see the brass actually is the alloy which is made of copper and zinc, where copper is the transition metal, zinc is not. And then we have bronze, where copper is the transition metal, but tin is a p block element, tin is not. Now we shall move to the next question, which is the different kind of important transition metal compounds. So first one is the typical chromate dichromate solution. So here we are giving the two structures. So draw the structures of chromate and dichromate ions. So here you can see chromate is CrO4 2-. You can see the structure here where chromium is attached to it 4 oxygen atoms. And here you can see the dichromate structure. So dichromate also has this butterfly kind of structure where there is an oxide bridge between 2 chromium atoms. Both of these ions are actually di-negative. So both the compounds are actually very much well known. In case of chromate, the compound is potassium chromate, which is depicted as K2CrO4. And the other one, that is a dichromate, it is also available in its sodium and potassium salt format. So the potassium one is most well known, which is K2Cr2O7. Both of them have their sodium analogous parts also. Now, these chromates are actually very much strong oxidizing agent, and they are actually very much important chemical which is used as an oxidant to prepare many azo kind of compounds. So dichromates are actually prepared from their corresponding ferrous chromate salt. When they treat their ferrous chromate salt with sodium carbonate in presence of oxygen, they form the sodium chromate. And when this sodium chromate will be acidified, we will have the sodium dichromate solution that will be crystallized. So in this case, you can see the structure of the chromate and dichromate here. So in case of chromate, the structure is actually tetrahedral. And in case of dichromate, the structure is tetrahedral units too, but they are actually held tight between the two units by the aid of this oxide anion. So this CR-OCR bond angle is 126 degree. And the bond distance between this chromium and this oxygen atom is 180 picometer almost. So you can see both of these chromate and dichromates are tetrahedral, but in case of chromate, there is a single tetrahedral unit, but in case of dichromate, two tetrahedral units are actually connected one by one CR-OCR, that is chromium O chromium linkage. So this potassium and this sodium dichromate both are actually very strong oxidizing agents. The sodium salt has some higher solubility in water, and that's why that is extensively used as an oxidizing agent in the organic industry. But in case of potassium dichromate, this K2Cr2O7 is also important in some other aspect. It is actually used as a primary standard in the volumetric analysis. So what is meant by this primary standard? So the primary standard reagents are those reagents whose concentration does not change with time. So if we prepare a specific, suppose 1 molar K2Cr2O7 solution, so after some 20 days or 30 days or 6 months, the concentration will remain the same. That is called the primary standard solution. So potassium dichromate is actually used as a primary standard solution in the volumetric analysis, where specific concentration is actually required. This is actually used to calculate the exact normality or the molarity of the solution. So here there are some informative questions that are actually taken up. First one is what happens when acidified dichromate solution is allowed to react with Fe2 salt. So I have already told that this dichromate is actually a very strong oxidizing agent. And you know this iron 2 is readily oxidized to iron 3. So here you can see in case of dichromate, the oxidation state of chromium is +6. And in this case, the oxidation state of chromium is +3. In iron 2, the oxidation state is +2. And in iron 3, the oxidation state is +3. So from chromate to chromium, it is actually a reduction that is taking place. And from iron 2 to iron 3, it is an oxidation that is taking place. So basically, it is a redox reaction in acidic solution. So Cr2O7 2- is having reacted with 14 moles of H plus and 6 moles of Fe2 plus to produce 2 moles of Cr3 plus, 6 moles of Fe3 plus, and 7 moles of water. So this is the balanced equation for the Fe2 plus oxidation by acidified dichromate solution. So this acidified dichromate is having a very strong oxidizing action. So if we can draw the oxidizing action of a dichromate, you have to see, suppose it is dichromate here, which is as Cr2O7 2-. It is reacting with 14 moles of H plus. So firstly, we will not balance this equation. Firstly, we will see how the molecules are actually reacting, and then eventually we will balance it. So here it is having for Cr2O7 plus H plus it is having electron, because since it is oxidizing agent, so it will actually take up the electron. And since it is an aqueous solution, so we will actually add water on the product side. So now we will see here from dichromate we are having chromium 3. H plus is actually reduced to water because H plus is the oxidizing agent. H plus is actually reduced to. So here you can see here chromium 2 O7 2 minus is reacting with proton in presence of electron because it is an oxidizing agent. Is an acidic solution. The products are Cr3 plus and H2O. So first we will see that there are 7 oxygen atoms here on the left hand side and 1 oxygen in the right hand side. So firstly we will, to balance the equation, we will write 7 here. So 7 oxygens are here. By writing 7 oxygen, it is having 14 protons. So because 7 into 2 is 14. So we write 14 here. So H plus is balanced. Oxygens are balanced. Now you can see here in this case, the net charge here is 14H plus is counteracted by electrons. So here you are having 14H plus, we are having 1 electron and di-negative charge. So total we are having here. So in this case you can see here the electron, 1 electron and 2 electrons are here 3. So 3 and minus 14 is actually 11. So 11 positive charge is there in the left hand side. But on the right hand side there are actually 3 plus charge. Since the chromium atoms are 2 in number, so we will first balance chromium here. So we will write 2. So we are having net 6 charge here, but here in this case the charge is not that because we are having 14H plus, then we are having this 1 from this electron and 2 from the oxide. So we will have 14 minus 3, that is 11. So on the left hand side we are having 11 positive charge. On the right hand side we are having 6 positive charge. So 5 positive charge should be balanced. So that's why we will add 5 electrons here. So it will be written as 6. So now you can see 14H plus 6 electron and 2 electrons from this. So 8 electrons. So 14 minus 8 is 6. So plus 6 charge on the left hand side and plus 6 charge also in the right hand side. So that's how the equation of potassium dichromate acting as an oxidizing agent is balanced. So this is the balanced equation for oxidation by potassium dichromate. Now the E0 value of this specific reaction is actually very high, which is 1.33 volt. That's why potassium dichromate is one of the very strong oxidizing agents. Now in acidic solution, this potassium dichromate is actually able to oxidize iodide to iodine, sulfides to sulfur, also tin 2 to tin 4. So there are typical examples where this dichromate is actually able to oxidize different species. So I minus to I2 is occurring. From sulfide, it actually produces sulfur. From stannous 2, it forms stannic 4. So from SN2, it can oxidize SN2 to SN plus 4. It can also oxidize iron 2 to iron 3, which example I have depicted here. So now we are actually going to the next question, which is regarding potassium permanganate. So potassium permanganate, what happens when KMnO4 is heated at 240 degrees Celsius? So when KMnO4 is heated, thermal decomposition takes place at 240 degrees Celsius. So what are the products? So when KMnO4 is heated, it actually forms K2MnO4 and MnO2. In KMnO4, the oxidation state of manganese is +7. It is also very strong oxidizing agent, and the structure resembles as that of chromate. its structure is also tetrahedral. You can see here that I am drawing the structure for you. It is MnO4 minus, which is having a tetrahedral structure, just like the chromate. The oxidation state of manganese is +7 in chromate. That's why it is a very strong oxidizing agent. Now, when KMnO4 is heated, the thermal decomposition takes place and the products formed are K2MnO4, that is potassium manganate, MnO2, that is manganese dioxide, and oxygen. So here the oxidation state of KMnO4 is +7. Oxidation state of this K2MnO4 is +6. And that of MnO2 is +4. So here from +7, both the reduction takes place. Both kind of reduction. So the first reduction is 1 unit reduction from +7 to +6. And second one is the 3-section reduction from +7 to +4. So thermal decomposition occurs from +7, a +6 compound, that is K2MnO4, and another is +4 compound, that is MnO2. These are actually formed. So this MnO4 minus or KMnO4 is a very strong oxidizing agent. Now what happens in lab? In lab, manganese 2 salts are taken and they are actually oxidized by potassium disulfate in aqueous solution to produce this kind of permanganate. Now this permanganate, when we are having this is MnO4 minus, and when you are having this manganate is MnO4 minus. So in manganate, the oxidation state of manganese is +6, but in permanganate it is +7. Now the last question is, show the oxidizing nature of permanganate in acidic and neutral or faintly alkaline solution. So this permanganate is also capable to show oxidizing property in both acidic solution as well as neutral solution also. When the solution is faintly alkaline, then also MnO4 minus can show its oxidizing property. So the first one is in acidic medium. What happens? In acidic medium, 5 moles of nitrite, that is NO2 minus, will react with 2 moles of MnO4 minus in acidic medium, that is 6H plus, and it will produce 2 Mn2 plus, 2 moles of Mn2 plus, 5 moles of nitrate, and 3 moles of water. So here you can see the manganese state is +7. So from +7, it is actually reduced to +2. And in case of nitrite, the oxidation state of nitrogen is +3. But in case of nitrate, the oxidation state is +5. So here you can see, so 5 unit of reduction takes place of 2 moles of manganese. So that's why it is a net -10 reduction in the oxidation state. And in case of nitrite to nitrate, you can see from +3 to +5. So 2 units of oxidation have taken place on 5 moles of nitrogen. So it is also having increment in the oxidation state. So +10 -10 will be cancelled out to 0. So from nitrite, we are getting nitrate. And from Mn +7, we are getting Mn +2. This is an oxidizing property of permanganate. And what happens in the neutral medium? In neutral medium, a manganese 2 will be actually oxidized to MnO2. Basically, this is a kind of comproportionation reaction. Here you can see the manganese state is +7 and the oxidation state of manganese is +2. And both are actually going to the oxidation state of +4. So when 2 different oxidation states merge into one oxidation state, that is termed as the comproportionation reaction. Now the presence of zinc oxide and zinc sulfate actually catalyzes this very reaction. So from Mn +7 and Mn +2, both are actually going to +4. So this is actually a reduction of MnO4 minus, but the oxidation of manganese 2 plus. So with this, the chemistry of D and the F block elements are over. So now we shall move on to the next chapter, next part of this session, that is the F block elements, chemistry of F block elements from the next session. And with this, we will have an end on the chemistry of D block elements.